Hey kids, do this problem. Good job. Due to the third law, it's 400 newtons. 800 newtons is the man's weight. 600 newtons is the cart's weight. Those are not relevant. If the man exerts a 400 newton force on the cart exerts a 400 newton force in the opposite direction on the man. That's just Newton's third law, which we learned last lesson. So now we're going backwards. Third law, second law. Second law is much less conceptual than third law, and it's much more important. It's the most important thing we've learned so far. It'll be the most important thing. It's probably the most important thing to learn in the class. So make sure you get it right. A force, by definition, is a push or a pull. If you think of like Star Wars, the Jedi can like push their droids, or they can pull like a lightsaber. Like when Luke's like hanging upside down on Hoth, and he's gotta like cut himself free. He pulls the lightsaber and chops himself free. No spoilers, by the way. That movie's like 30 years old, so it's fine. Like 50. Oh, I'm so old. It's a very old movie. A force is a push or a pull. Any push or a pull is a force. Think about an object moving. Let's say just a rock is flying through space, like a comet, like an asteroid, whatever. There's some rock floating through space. The rock has some mass, because rocks have mass. Duh. What does a force do to a moving rock? Tell me in your own words. What does a force do to a mass that's moving, already moving? It's really important to imagine something that's already moving, and it's in space where there's no gravity, no air resistance. If we are in space where there's no gravity, no air resistance, no friction, no nothing, an object that's moving will keep moving. But if there's a force on it, it could speed up, it could slow down, it could also turn, change direction. Anything can happen. One word or two words that can summarize all three of those, speeding up, slowing down, or change direction, we could say a force will change velocity. And another word for that, a change of velocity, is known as an acceleration. Forces cause change and acceleration. That's Newton's second law. It's not just any force. Like if I have a baby in my hand, there's two forces on the baby. Normal force upward and gravity downward. But the baby's not accelerating unless I drop it. It's not force, it's net force or total force. Imagine you have a big net, you scoop up all the forces, that means it's a net force. Some people write F net. I like to write sigma F, the summation of F, because it's Greek, makes it sound real smart. F net equals M times A. We already talked about mass. We said mass gives an object inertia. Inertia is resistance to a change in motion, a change in velocity, or acceleration. This equation states that very clearly. The total force on an object will cause it to accelerate, and the acceleration will be based on the force and the mass. If you want the acceleration by itself, it'll be the net force over the mass. They're both vectors, so sometimes you give them one like vector hat. But if I add up all the forces on like a rock, and I say, oh, this 2 kilogram rock has a total of 10 newtons of force west, it'll accelerate 5 meters per second west. That's Newton's second law, the most important equation of the entire year. So read it over, it makes sense. Let's look at this picture. This is a really important lab we would have done if we were in person. It's called a half Atwood machine. Basically, a mass on a frictional surface, usually a cart with wheels, is pulled by a string, and the string is tied to a hanging mass, I guess. So The hanging string, the weight on the string pulls the cart sideways. You have to assume the string doesn't stretch, the string has no mass, the pulley has no mass, the pulley has no friction. You have to assume a lot of things, but this is a very common physics setup that we'll talk about a lot. The pulley pulls the cart sideways when the weight falls down. We're not going to do these problems, we're just going to see this picture. So how do we solve this problem? I'll show you guys right now. Yeah, okay. So the half-hour machine. There's a cart. I'll call it capital M. There's a pulley. And there's a cylinder. Normally call this the hanging mass, but we're going to talk about masses a lot. So I'll call it a cylinder. Big M is the cart, little m cylinder. You set this up, and you just let go of the hanging mass, and you find the acceleration. How do we do this? Let's do a real easy problem first. Let's assume the string was cut. Now I'll draw a free body diagram for the cylinder. If the string was cut, there's no upward force. There's only a downward force. Fg is m times g. And then let's use Newton's second law to find the acceleration of the cylinder. A cylinder equals F net over m. Well, there's only one force on the cylinder, Fg. That is m times g. So, if the string were cut, the cylinder will accelerate downward at g 9.8 meters per second squared, which is what we already knew. So we're good so far. Excellent, awesome. And this works for anything in free fall. If there's only one force, Fg, then the acceleration comes out to just g, which we already knew, but now Newton's second law confirms that idea. And this is very common in physics. You'll learn more rules that confirm the old rules, but also teach you more stuff for more complicated scenarios. So let's do this complicated scenario where the string is still there. So we're on the free body diagram for the cylinder. Fg is the same. Now we got Ft. Here's an AP free response question. Is Ft going to be bigger, smaller, or the same as Fg? Tell me right now. Is Ft going to be bigger, smaller, or the same? Sage, what do you think? The same. Well, it's not. If Ft and Fg were the same, or they were equal in magnitude, or they add up to 0, there would be no net force on the cylinder. But that would mean, according to the second law, that the cylinder will not accelerate. But the cylinder will accelerate. When you let go of this situation, the cylinder will accelerate downward and will pull the cart sideways. That's just like how the setup is built. So Ft is less than Fg, and the mass will accelerate downward. Okay? Great. Now a free body diagram for the cart. We don't know anything. We can't solve this, but watch this. The cart's free body diagram. We got Fn, the normal force from the table. Fg, the weight of the cylinder. No, the weight of the cart, not the cylinder. And this sideways force. Should this sideways force be Fg or Ft? If you pay attention last lesson, you'll realize, oh, the sideways force is Ft. Since the hang mass pulls on the cart, no, since the cart pulls on the hang mass with force Ft, the hang mass pulls on the cart with force Ft, not Fg. The pulley basically takes that force and turns the direction, if it's an ideal pulley, and that's what we're going to assume. So ignore the weight of the pulley, the mass of the pulley, the forces on the pulley. Just say, oh, the pulley just turns the force sideways. So the mass, so the cart is pulling the cylinder is pulling the cart with the same force, Ft. We don't know what's happening now, but we do know Fn and Fg will cancel. Ft is the only force, the net force, therefore the cart must accelerate sideways. How do we solve this problem? I'll show you guys the trick. Solve this for A. Now realize the forces, the acceleration of the cart and the acceleration of the cylinder are going to be the same. They'll be the same magnitude. They won't be the same direction. Obviously one's right, one's downward. But they'll be the same magnitude if they're tied together and the string doesn't stretch. So they're the same acceleration. F net over m for the cart equals F net over m for the cylinder. Do I have space for this? Let me erase this free ride diagram. But the free ride diagram, hopefully it makes sense. I have some space over here. I'll just scooch myself. Okay. A equals F over m for both objects. So A equals, let's do the cylinder. F net. We said Fg is bigger than Ft. So F net is Fg minus Ft over m. Now look at the cart. There's only one force, so it's Ft over capital M, because capital M is the mass of the cart. Now we do, physics stuff. If these are equal, we can cross multiply. Oh, I'm also going to substitute Fg. This Fg is on the cylinder side, so it's the cylinders. Okay, we're not really going to solve. You could solve this if you had numbers and variables and stuff. But, I mean, what do you even want to solve for? I guess you can solve for Ft. That's not really what important what you solve for. The important idea is they have the same acceleration. So this equation, this setup right here, is the important step. But I solve for Ft just because I felt like solving for stuff. I guess I have no life. I just do physics all day. This would be Ft. And if you found that, you could find A for this equation. That's second law. Let's take a quick break for me, not for you. You guys do this problem. It's not 4. Don't choose that. Okay, you got it? The word constant is there to trick you. Yeah, it's a constant force. And we learned force, or net force, is mass times acceleration. In this problem, the force is constant, and it is the net force because it's in deep space. So the force is constant. People think, oh, well, F is constant, A is constant because F equals ma. Almost. F is constant, but the rocket burns 1 kilogram of fuel every second. So its mass is decreasing. If F equals ma, or F net equals ma, the force is constant, but mass decreases, acceleration increases. Wow, mind blown. Crazy, yes. This is a very important thing to realize if you work for NASA. Most of the fuel on like a rocket ship, a spaceship, is burned up by the time it gets to space. Remember, like there's like a little white space shuttle, and a humongous like orange rocket, and then like 2 small white rocks on the side. Those like thrusters kind of fall off during flight. Most of the mass of the space shuttle is fuel used to carry all that mass into space. So it's a very important idea for rocket scientists, which you guys could be because you're so smart. So that's a great thing to think about. I think we're almost done with this idea. Yeah, let's keep it a little shorter than yesterday. One last important idea. You guys ever play volleyball? Hopefully you have. That's what volleyball's like. You guys ever go bowling? Hopefully you know what bowling is. Let's say school goes back in person and all the teams are super excited to go play in their games and tournaments. And there is such a rush to get ready for their big game that the volleyball team and the bowling team switch bags, and the volleyball team has to play volleyball with bowling balls, and the bowling team has to bowl with volleyballs. What's going to happen? Explain what's going to happen in this problem. What happens if you try to play volleyball with a bowling ball? What happens when you try to bowl with a volleyball? And how does that relate to Newton's second law? Okay, obviously the answer is it's bad. It's not good. It's bad. When you're trying to play volleyball, you usually like bump the ball with your arms like this, or you set the ball with your arms like this. You want to accelerate the ball. So it's got to have a small mass. If you're applying a force on a volleyball, you want to accelerate it. So the smaller the mass, the more acceleration. A bowling ball will not accelerate. So if the bowling ball is coming down like this, and you put your arms out trying to bump it, it's not gonna accelerate. It's gonna keep going. It's gonna go right through your hands, and you're gonna be very sad. So obviously the volleyball team is gonna have a sad time because it's harder to accelerate a bowling ball than a volleyball. Similar for the bowler who's using a volleyball, the problem switched. The bowler wants to knock down all the pins, not just one. That's what pins look like. In case you didn't know. Good job drawing these pins. Thanks, Michelle. When the ball hits the first pin, does the bowler want it to accelerate and change velocity? They don't. They want it to keep going with the same velocity. They want the ball to hit one pin and keep going, hit the second pin, keep going, hit all the pins, and keep going the same way. Or at least they don't want the velocity to change very much. If they bowl the ball pretty fast, they don't want it to slow down significantly whenever it hits a pin. So they want less acceleration after it's thrown. That's a key difference. They want to accelerate it while they're rolling it, but after they roll it, they want it to keep rolling through all the pins. So they want it to not accelerate when it hits the pins. If it has less mass, like a volleyball, it won't be as good. So they both have a tough time. Very sad for both these athletes and sports enthusiasts. Bye.